Hi everyone. Once again, as with our statistical significance lecture, this practical significance lecture is going to recap the stuff we talked about in person this week, again so that you have multiple exposures to it and multiple opportunities to try and help make it stick. And it's also just helpful to, I think, hear it explained multiple times so that you pick up on different things each time. So the learning goals for this particular lecture are to first understand the basic procedure for each statistical analysis of an HST, essentially pulling together all of the previous weeks that we've talked about univariate, bivariate, multivariate, and inferential statistics into the procedures we need to know. And then also understanding the difference between statistical and practical significance, because I think a lot of times in these introductory courses we can get really hung up on statistical significance and miss out on meaningful discussions of practical significance. So we'll emphasize that here. So let's start by reviewing all of the pieces of analyses that we have talked about so far, so we can tie it all together and hopefully simplify the steps that you're going to be expected to implement each time you're conducting a statistical analysis. So first, we've talked about analyzing relationships. This occurs when we have a continuous IV and a continuous DV, most often when we have survey data that we're analyzing. We've talked about bivariate analyses, like Pearson's correlation, as well as multivariate analyses, like multiple regression, which allows us to account for confounder variables in those analyses. We have also talked about analyzing differences. This occurs when we have a categorical independent variable and a continuous dependent variable, most often with experimental data. We've talked about bivariate analyses with a t-test, and a multivariate analysis with ANCOVA, also known as an f-test. This allows us, again, to account for confounder variables and also, importantly, include more than just two groups in the analysis that we're conducting. When we actually conduct a null hypothesis significance test, it's important to emphasize that all analyses follow the same steps. You're going to get two scores, a test statistic, and a p-value. The first thing you want to do is interpret that p-value. Is the result statistically significant or not? If yes, you then move on to interpret the test statistic, the correlation, the beta coefficient, the t-test, the f-test. If not, you assume that the relationship or difference is zero. We have support for that null hypothesis. The relationship, the Pearson correlation, the beta coefficient are zero, or the mean difference, the t-test, the f-statistic are zero. And you can consider running analyses in sequence, as we've previewed previously. A bivariate analysis is going to tell us whether there's a relationship or difference between an IV and a DV. And multivariate analyses are going to tell us whether those relationships or differences change after we've controlled for confounder variables. So do we come to similar or different conclusions once we've run these sequences of analyses? So again, always follow the same steps. When we run that analysis, what is our p-value? Significant or not? If yes, look at that test statistic. If no, we assume the relationship or the difference is zero. Beyond that, we want to run our analyses in sequence, usually starting with a bivariate analysis and then moving on to a multivariate analysis. We've been emphasizing here so far this notion of statistical significance. This is what our NHST provides, our null hypothesis significance testing is providing. And what it tells us in plain language is that are the numbers we've identified in our sample big enough to reject our null hypothesis? Do we have evidence that kind of leans toward our research hypothesis? The important thing to note here, though, is that p-values are really heavily influenced by sample size. Significant results are much more likely to emerge in larger samples. And I mean that by saying statistically significant results are much more likely to emerge in larger samples. We don't need to get into the math behind it, but it's just important to know that the bigger the sample gets, the more likely you are to have significant results, statistically significant results, even potentially when those results are kind of meaningfully or practically meaningless. When we think about practical significance, we're asking, do our findings have real world importance? Do we have evidence here that matter so much that we should make decisions around them, change our lives around them, make policies around them, make rules around them. In other words, are the numbers we've identified in our sample big enough that we should actually care about them? Because rejecting the null hypothesis and obtaining evidence indirectly for our research hypothesis is much different. It's kind of more mechanistic, more mechanical, than deciding whether or not we should do something about those analyses that we've run. Should we actually make policy decisions, make life choices around these numbers that we found? And so we want to try and figure out a way to put some numbers to practical significance so that we don't just kind of have to make these decisions based on feelings or based on vibes. We can actually have some kind of numeric evidence or backing to make these decisions. So when we're thinking about practical significance, we're often looking at a third number, so not our test statistic, not our p-value, but a third number called the effect size. And this is the magnitude or strength of a phenomenon. When we're thinking about relationships, it's identifying how strong the relationship is between the IV and the DV. And when we're thinking about differences, it's showing us how large the difference is between two groups. And this is important because it's telling us not only do these numbers differ from zero, but just how strong, just how well do these kind of numbers go together? How consistently do these relationships emerge? How consistently do these differences emerge? And are they so consistent and large and meaningful that we should make life choices around them? Now, the effect size you use, of course, is going to be tricky, going to differ depending on the analysis that you've run. For relationships, we use something called R squared. For differences, we use something called Cohen's d. The good thing is that the judgments you're making are going to be very similar in both cases. And although I'm about to show you a bunch of numbers, I'm going to give you all of these benchmark numbers on the exam. So you do not need to memorize them. You just need to be able to compare numbers to these benchmarks and make some conclusions based on those comparisons. So although I'm going to throw a lot of numbers at you, you don't have to memorize these numbers, but I want you to understand the basic idea of what we're doing with the effect size. So as I said, the effect size for relationships is this R squared number. It tells us how much variance the independent variable explains in the dependent variable. In other words, how much of the variance in the dependent variable is explained by the independent variable. It's calculated very simply. When you run a Pearson's correlation, you get an R, and to get the R squared, you just multiply R by itself to get the variance explained. Now, I'm not going to ask you to do that in your exam or anything. So for this class, you can really just focus on R. So I'm going to show you the benchmarks for R squared and then also convert it into R. And we're really just going to emphasize these R values as a way to say you can run your bivariate analysis, you can run your correlation test, and you can get your R value, your P value, and that R value can simultaneously tell you two things. It can tell you the direction of a relationship as well as the effect size strength of that relationship. So it's really just intended here to simplify it a bit for you. So in the social sciences, we have different categories or different benchmarks for effect sizes. The smallest are what we call negligible, or basically 0, nothing kind of effect sizes. For R, it's going to range from 0.00 to 0.09. And what this means in R squared terms is that the independent variable explains less than 1% of the variance in the DV. Small effect sizes are going to be R from 0.10 to 0.29. When you square those values, it means the IV explains 1% to 8% of the variance in the DV. Medium is R equals 0.30 to 0.49. This would mean that the independent variable explains 9% to 24% of the variance in the DV, again, just squaring those values. And then finally, large is going to be R of 0.50 and up. If you'll recall, R can range up to 1, even down to -1. In this case, when you square these, the IV explains up to 25% and up of the variance in the DV. When we're looking and interpreting the effect size for R, directionality doesn't matter. So these could be R of -0.1, -0.29, -0.3, -0.49, -0.50. Doesn't matter. We're just looking at the strength of the relationship, the magnitude of that relationship. And so we've kind of run multiple correlations, looked at many examples through the semester. This is just now a way of saying when you look at that number of R, you can start to think to yourself, what should I be kind of benchmarking as pretty small, small, medium, large? Next, I'll try to show you some pictures that kind of visually help you understand what is a negligible relationship versus a medium or large relationship. So I pulled this image from a study to show you what a large effect size would look like, and it's kind of an obvious large effect size. So what we have, our independent variable on the x-axis here is showing us how many minutes students in high school were assigned of homework each night, each day. And then on the y-axis, our dependent variable is how much time they have spent doing homework. So you can imagine the more homework you're assigned, probably the more time you're going to spend doing homework. Pretty obvious. Though there's going to be some variation there, that just because one student was assigned a lot of homework doesn't mean they're going to spend quite as much time as another student who was assigned the same amount of homework. You might not do your homework at all. You might do extra homework. I don't know, whatever it might be. It's not going to be a perfect correlation, but we would expect these numbers to be pretty strongly related, that the more homework you're assigned, the more time you're going to spend doing homework. And that is, in fact, what we see. If you run this analysis, you can see we have this sloped line, and all of these data points are pretty closely clustered around this line. So as we've noted before, the more that these data points are clustered, the stronger the relationship we're tending to see. Numerically, what this looks like is an R value of 0.66, which is in that large category of those benchmarks we just looked at. The R squared value being 0.43, in other words, 43% of the variance. So a way of saying this is that knowing how much homework you've been assigned, I can explain about half the variance and how much time you're then going to spend doing homework. So knowing how much homework you're assigned, I can predict with pretty good accuracy how much time you're going to end up spending on homework with these kind of analyses that I could conduct. So this visually, I want you to see, is what a large effect would look like in social sciences. What's interesting, though, is that small effects are actually the most common kinds of effects that we have in the social sciences. So this is just pulled from that same bivariate calculator that we looked at before to kind of try and visualize different types of correlations. This is just to show you what a small correlation would look like. So this is the smallest benchmark for what we would call not quite a negligible effect size, but a small effect size, an R of 0.10. In this case, an R squared of 0.01, which is explaining about 1% of the variance in an outcome. And this is quite small. You can see barely any slope in this line. Data points very much scattered about this line. We're not explaining a ton of the variance in the outcome. But I want to emphasize that in social science research, these are often the size of the effects that we're talking about. When we're looking at things like social media use and different kinds of negative outcomes, these are the kinds of effect sizes we're talking about. And so the question for us becomes, to what degree do you want to decide to make policy and change your life around these kinds of small effect sizes? How confident are we in them? Are they super really small? Are they in that medium range? When we're getting to these really large effect sizes, we're getting more into these very kind of obvious comparisons, like, oh, the more homework you're assigned, the more time you'll spend doing homework. When we think about effect sizes for differences, we're thinking about what's called Cohen's d. And in plain language, what this means is it's telling us how far apart are the means that we're actually comparing when we run these t-tests. When we compare these different mean distributions, about how far apart are the means. And we base it not just on the numeric difference between mean 1 and mean 2, but it's based actually on the standard deviation. So how dispersed are the means from one another? Not just how far apart they are, but how dispersed are they based on dispersion that's present in the data. So in the social sciences, we're again going to have this same kind of 4-category benchmark of negligible to small, medium, and large. Negligible ranging from d of 0.00 to 0.19. In plain language, that'll mean the means are really not that different. A small effect, a small difference of d of 0.20 to 0.49 means that the means differ by 0.2 to 0.49 standard deviations from one another. Medium of d 0.5 to 0.79 means the means differ by 0.50 to 0.79 standard deviations. And large meaning d of 0.80 and up, meaning that the means differ by 0.80 or more standard deviations. And again, directionality doesn't matter when interpreting effect sizes. If these D's are negative, it's just a matter of which mean did you subtract from the other one. So depending on which way they come in the equation, but the D itself, the Cohen's D is going to be same regardless of which way you subtract them. So again, just like with R, the directionality you can ignore in this case. So this is an image we looked at a few weeks ago, I believe, when we were talking about t-tests. And this was an example we put up to say, like, let's imagine this distribution of men's heights versus women's heights. And we can see, you know, there's some degree of overlap between these distributions, but we can see these mean scores of men's heights on average being about 5 inches higher than women's heights. And despite the amount of variance that we see kind of within each of these distributions and even the degree of overlap we see within them, we can kind of tell that these are two different distributions rather than two quite overlapping distributions. When we put this into plain language, this is a mean difference of about 5 inches and a Cohen's D of 1.72. So that means that these means are differing by almost 2 standard deviations, which is pretty huge. So we said a large Cohen's D was 0.80. This is almost twice that size. So visually, I want you to see this and recognize this is a huge, massive difference. So when we're looking at group comparisons, when we're looking at visual comparisons of these groups, this is what a huge, massive difference will look like. We're not really ever going to see mean differences larger than this kind of mean difference. So you then might ask, well, what does a small effect size look like? So here's a Cohen's D effect size of 0.2. You can see these distributions are essentially entirely overlapping. We're getting very kind of minuscule differences between them. But often in the social sciences, small effects, again, are what we're working with, what we're dealing with. So we don't often get those massive kind of differences that you saw in that first picture. We're often talking about these teeny tiny little differences. Now, the question often when we're deciding what to do with that information is it like really teeny tiny difference, or is it kind of like a medium difference? And to what degree, what situation am I thinking about this? And is it something that I actually want to base my life around, base policy around, and so forth? But the important thing I'm hoping that you recognize here is that even when we have statistically significant effect sizes and differences and relationships in this research, we're often talking about these kind of small relationships and differences. Another couple points to take away here is that in large samples, meaningless differences can be statistically significant. So even really teeny small effect sizes, sometimes even in those negligible effect sizes, can be statistically significant in those samples. So it's really vital to look at effect sizes when interpreting the results of any research study. And I say this to mean, like, particularly when we have significant results, you want to look at the effect size because you want to know, are we talking about really weak relationships, somewhat small to moderate relationships, or large relationships, or differences, whatever it might be. But particularly in cases when we have non-significant findings, the inverse is also true, that it's more difficult to get statistically significant results in really small samples. And so when we have non-significant results, particularly in small samples, it's really useful also to look at the effect size to see, well, despite the non-significant results, are we still seeing kind of meaningfully sized effects? Is there seem to be something there worth looking at despite the small sample, despite the non-significant results? You don't have to worry about that for your exam setting, but I just pointed out to say that we often get caught up quite a lot in statistical significance, and there have been a lot of arguments more recently to say we really should be emphasizing practical significance as much, if not more, than the way that we emphasize statistical significance. All right, and so just revisiting these learning goals for this particular lecture, we want to understand the basic procedure for each statistical analysis. Again, really emphasizing that p-value for making that initial judgment of do we have evidence for or against our null hypothesis. And then also understanding the difference between statistical and practical significance. Understanding that we have these measures of effect size for t-tests and for Pearson correlations, and these benchmarks we can use to interpret what those effect sizes look like. You do not have to memorize, again, the effect sizes. I will give you those effect sizes on your exam. I want you to just understand how to evaluate effect sizes relative to the benchmarks that you're provided.